Hello everyone, welcome back to our lecture, where in this final chapter number 8, we will discuss on the applications of finite elements method in solving or modeling heat transfers problems in thin fins. Fin is just an extended surface that we may find attached to the body of a system that generating heats. For example, we may find a fin which is fitted around a motorcycle engine block as shown in the figure. So the main purpose of the fin here is actually to enhance further the heat removal process from the body that generating heat by extending the surface of the main body, which are exposed to the air or to the cooling fluids. So that's means here the bigger area that is exposed to the air and more heat can be removed from the systems. We also may heard that the performance of mechanical systems or some of the electronic systems often influenced by the temperatures. For some applications, working at high temperature conditions will degrade the performance of that particular system. Thus, in this topic, we would like to use or to look at how we can use the finite element model, finite element method to model this, to model and analyze the heat transfer process occurs in thin rectangular fins. So in fact that fin itself can be found in various shapes which is other than rectangular shapes. Some fins you may find designed in a cylindrical shape. Some of them you may find that came in a tapered cylindrical shape or tapered kind of plate shapes, and many more. Thus, the objective of our study now is limited to the modeling of the heat transfer, temperature distributions, and also the heat dissipated by this rectangular fin. But the similar process occurs on these other type or other shape of this fin. It's just the matter of the for the rectangular thin fin, the area will be constant, the surface area will be constant from the root to the tip of the fin. We also limit our discussions on one-dimensional heat transfer in this thin fin, where if we consider a single fin as shown in these figures, one-dimensional finite elements will be used to model how much the heat will be transferred from the base body, which is located there, into the ambient air. And since we are considering a one-dimensional problem as well, then the temperatures, the only temperature distributions in the length directions of this fin, which is taken from this base from the root to this tip of the fin, will be taken into considerations. To solve the heat transfer to the fins, the similar governing equation that we developed in the when we're solving the heat transfer through the plane wall, the similar governing equations still can be used as shown by equations 8-1 here, where if we can recall back these governing equations, we know that Q, the capital Q here, is actually equal to the Q over dx, or the gradients of the heat flux per unit area in these x directions, since we are considering only one-dimensional problems. And the heat flux itself is governed by the Fourier's law, which stated that Q, which is equal to negative K, where K is the thermal conductivity of the material, then multiply the gradients of the temperature in these x directions. But for the fin problems, usually this the K or the thermal conductivity will varies along the x directions, taking, for example, from the base point here toward the tip, then the K usually varies along this through the length of these fins. But again, here we limit our discussions by considering that the material we use in our problem is isotropic and homogeneous, which is here means that the K will be uniform and has the same value in all directions. Since we are interested in modeling the heat transfer through this fin from the base here to the tip, then we can develop the finite elements modeling to analyze or to predict or to model how the temperature will be distributed from the base to the tips. So for one-dimensional problem, actually we can discretize this fin from the base to the tip by several finite elements. And since the heat transfer through the thin fin is assumed one-dimensional, then we will model the fin using the one-dimensional heat transfers elements, where in this case, in the first figure here showing the fin, which is discretized into 3 elements, and model it in the global coordinate system. So this is the whole fin that we have. For example, if we can view, this is the base of our fins, and this is the fin itself, where we discretize it into 3 heat transfers elements, where of course we have to again to give these all the nodal points the numbering to all the nodal number to the nodes, to each nodes, and we have to establish this element connectivity between these elements and also the nodal points. So as a single elements, so we can write this in the local coordinates, where as usual, or as we discuss in other topics, for the finite element modeling, if we take only single elements and if we view it in the local coordinate system, which is in the z or in the natural coordinate system, then we can take that z will equal to -1 on the left nodal points, and z will be equal to +1 on these right nodal points. So that means if we would like to know what is happening there, which is actually reflect to the z, which is equal to 0. In modeling the heat transfer using finite elements, our system of linear equation will be in the form of k t, which is equal to r, where if we solve these simultaneous equations, then actually we will get the value for the temperature, which is in priori, we do not know this value t. So once we solve this kt equal to r, actually we are predicting the temperature at each nodal points. So in many cases, sometimes we also need to know, or we need to predict what is happening somewhere there, which is the location that resides in between the two nodal points, where the temperature is at this stage we still do not know the temperature at that particular point. The temperature that we obtain from the system of linear equation, which is actually the temperature that resides exactly on this nodal point. So the simplest way to obtain the temperature that the unknowns of value of temperature that reside in between the two knowns temperature obtained from the system of linear equation is by solving the interpolations between the two knowns value. So this process will be applied in this heat transfer process as well. So for simplicity, we will assume that temperature will vary linearly within the elements. So that means if this is my elements, so we expect that the temperature will vary linearly from one point to another point. So we expect, if we know the temperature here and there, so by taking the linear relation between the two, so we can roughly predict what is the temperature at that particular point that reside between the two known temperatures at each nodal point. So this can also be done by solving equations 8 2 here. So it says that the temperature field, which is written in the natural coordinate system, is actually equal to n1 t1 plus n2 t2, where t1 and t2 must be first calculated from this system of linear equations. n1 and n2 here is actually just the interpolations coefficients, which is known as the shape functions, and it's given as equation 8.3 here, where n1 equal to 1 minus z divided by 2, and n2 equal to 1 plus z divided by 2. So we know earlier that z is -1 on the left hand side, for the node that reside on the left hand side of our node of our elements, and the z which is equal to positive value of 1 and reside on this nodal a point that located on the right hand side of our elements. And again here, before we can solve the simultaneous equation kt equal to r, then we have to supply the elements conductivity metric for each element. So for solving this thin film problem in one-dimensional approach, so similar element conductivity metric as we use for solving plane wall problem can be used, and is given by equations 8, 4 here. For the element heat transfer matrix, in the thin films, heat is dissipated primarily by convection heat transfer. So most of the heat dissipation, heat removals from the fin is actually governed by these convection heat transfers through the flow of the cooling fluids or through the ambient fluids motions. So the effect of conductions through the fin is represented by the conductivity matrix KT. So to include the effect of convections heat transfer, then we need to establish the heat transfer matrix, which is given by H T. As we can see here in equation 8.5, HT is given by HL over 3 T and multiplied by this 2 by 2 square metric of 2112, where in this metric actually the material properties in terms of the heat transfer coefficient is included in this what we call it as the element heat transfer matrix. And other than that, the geometrical information in terms of the length of the elements and also the thickness of the fin are also included in this element heat transfer matrix. In thin film problem, there are two types of boundary conditions involved. The first one, which is known as the known or specified boundary conditions, temperatures value at the base of these of the fins. So considering this is the main body of our system that generating or having high temperature regions. So if we can imagine, if we put the temperatures or the thermometer on the surface of this body, then we can get the temperature on the surface of that of this particular bodies. So this T1 actually refers to the temperature on the surface of the body. So this is the first boundary condition that we have to deal with these thin fins. And other than that, which is if we take our fin as this single element, so this element will expose to the convection process. So the convection heat transfers boundary conditions or conditions is included in the system of linear equations, and is and it will reside on the right hand side of this equation where we have r here, and then this will be given by these equations A6. So the element hits rate vector r infinity. This equation is applied to a single element, so we have to solve this equation for each element that we have. So this equation is given by HLT over small t and multiplied by 1 1. So where the H here actually refers to the convection heat transfer coefficients. L is just the length of the element, so length of this element from nodes number 1 until nodes number 2 in these figures. And we have T infinity, which is referred to the convection's temperatures or ambient temperatures, and the small t here is actually referred to the thickness of the fins. So in this particular topic, we limit our discussion to the rectangular thin fin that has what we call it constant thickness. So this effect is not that difficult to apply. So imagine that if we look in the cross-sectional area of fin with tapered geometry, then the thickness of the fin itself, if I can draw this in 3D, so the thickness of the fin will vary from the base to the tip here. So these equations cannot be applied for this particular problem, or we have to come up with the relation between the thickness as its progress in this direction if you want to apply into this equation H6 for the tapered type of these fins. The system of linear equation that we are going to solve for solving this heat transfer in thin fins, which is in the form of equation 7 here. So the equations contains the K plus H, which is the combinations of the conductions and convections, then multiplied by the T, which is the temperature that we are going to determine, and this all of this will be equal to the R, where R here came from the boundary conditions and due to the convection process. And we have the note at the bottom of the slide here says that if the fin is insulated, so if we insulate the fin, then the magnitude of both H and R will be 0. Now let's look at the thermal boundary conditions. As I mentioned just now, there are to solve the system of a linear equation requires us to specify the boundary conditions. So the first boundary condition is in the form of the known temperature at the base. So it's mentioned that temperature at the base of the fin usually refers to TB, is usually assumed to be the same as the temperature of the structure. So as I mentioned just now, if we put the thermometer on the surface of our structure, so we get the reading of the temperature on that particular surface. So similar, so if we place the fin on that particular point where we measure the temperatures, so the temperature at the base here for our fin will be the same as the temperature on that particular surface as we measure just now using the thermometer or whatever kind of thermocouple as well can be used. So the tip of the fin can be assumed as adiabatic or insulated. So this is the two conditions that we use in our assumptions. Therefore, the heat flux Q equal to 0 at the tip of the fins. Then hence the boundary conditions for the fins are we have the T at the nodes 4 here, or at the base, which is equal to T at the base, or we call it as the specified temperature. Y at the tips of our fin, then we have or we assume that we insulate the surface, the thin surface. So let's say this is the surface of our fin, which is spanning outward of the base surface here. So this is where we insulate it. Then it results to Q equal to 0. That means no heat flow through this the surface at the tip of the fins.